Hi, so let us continue the lectures on the vector analysis part, which we were discussing in the last lecture. So this is our lecture 2 in the series of electromagnetic theory. So in the last class, I discussed some operations on the vector which we can do, and I also defined what is vector, but we did not take any reference to which the vector was defined. We were just discussing about the vectors arbitrarily, okay? But it is often easier to set up a Cartesian coordinate system because often in the questions or in the problems, the vectors are defined in terms of their component along the x-axis, y-axis and the z-axis. So oftenly vectors are defined as a point or in the Cartesian coordinate form. Yes, so it is easy to set up some reference, and this reference would be our Cartesian coordinate system. Okay, so let's discuss or let's set up what is Cartesian coordinate system. We are familiar with the 2D x-axis and the y-axis. These x-axis and the y-axis are perpendicular to each other. Now, when we are talking about the 3D coordinate system, there comes a direction called g direction, okay? Now, there is a confusion or there is a ambiguity in choosing the direction of the plus or the positive z-axis. So, whenever you want to calculate the direction of positive z-axis, then you have to use the right hand rule. Okay, we also discussed about this rule, right hand rule, in the last lecture, but again let's look at it. So let's say this is my positive x-axis and this is positive y-axis. Then if you need to find which direction is your positive g direction, then you just have to point your fingers of right hand into the positive x direction and then curl around these fingers like as shown in this picture of hand. You just curl around your fingers into the direction of plus g direction, okay, plus y direction, sorry. Then the direction of your thumb would be the direction of positive g direction. So that is the right hand rule, or this coordinate system is also called right-handed coordinate system. And exclusively we will be using this coordinate system for our theory, which we will be laying out in further courses or in the further lectures, okay? Now, I also wanted to tell you one thing. Okay, that's fine. We have detected what is the direction of plus g. But let's say you are given the x and g and you need to find the direction of positive y-axis. Then also you have to use the right hand rule, okay? So this coordinate system or the direction of the x-axis, y-axis and the z-axis will be following the right hand rule. But from which vector or from which direction you have to start your curling around your fingers. So in order to get the positive g direction, we started with the x and we curl around our fingers towards the positive y direction. So there is a manner x-axis, y-axis and then z-axis. So this is the cyclic manner in which we have to go. So let's say we want to find the direction of positive x-axis. Then you have to start pointing your fingers from the positive y-axis and then curl around your fingers towards the z, and the direction of thumb would be giving you the positive x direction. Yes. Similarly, if you want to find the direction of positive y, then you have to start from positive z direction, okay, and curl around your fingers towards the positive x direction. Then the direction of thumb would be giving you the direction of positive y. Okay, so let me make it very clear because this is very important and we will be using this convention throughout. So we have to go in this cyclic manner which I am drawing here. Okay, so you cannot start from X and go towards the Z. Okay, you just have to start from X, then Y, and then Z. Okay, this is the cyclic manner in which you have to follow the right hand rule. Okay, that is fine. So we have set up our Cartesian coordinate system and we will be using this coordinate system only. Okay, now let's say these y cap, z cap and the x cap are the unit vectors parallel to the x by z respectively. Okay, now these are the unit vectors, so magnitude of these vectors would be 1. Now these vectors are also called the basis vectors. You can also read about the definition of basis vector, but basis vector are the set of vector in a coordinate system or in a vector space mathematically. With the help of these basis vector, we can make up any vector in that vector space. So these x cap, y cap and z cap so these x cap, y cap and z cap are the set of basis vectors in the 3D coordinate system. That means any vector, any arbitrary vector in the 3D coordinate system can be represented in the terms of these x cap, y cap and z cap. Okay, so this is the set of basis vector. So let's say we have any arbitrary vector A. Now we can make this vector in terms of these x cap, y cap and z cap, like in this way. Okay, so you can write any arbitrary vector in terms of x cap, y cap and z cap, any arbitrary vector in the 3D space. Okay, because this basis vector is for 3D vector space. Now what are these ax, ay and az? So often we are given a vector in terms of the coordinate. So you could be given this vector A in terms of ax, ay and az. Then these ax, ay and az are simply the component in the direction of x-axis, y-axis and z-axis respectively. Okay, so these are just the component along the Cartesian coordinate axis. In another way, I can also say these ax, ay and az are the projections. So like this ax, let's say this is my vector A, okay, and this is my direction of x-axis, which is represented by x cap. Now this ax, which I'm talking about, is just projection of this vector A onto the vector x cap. So let's say this A vector is given by ax x cap plus ay y cap plus az z cap. Now when you want to take the projection of any vector towards another vector, then I discussed in the last class, you just have to take the dot product. Okay, so when you will take the dot product of A with x cap, okay, so you will find it like ax x cap plus ay y cap plus az z cap dot x cap, and the dot product of y cap and z cap would be 0 because these are two perpendicular vectors and the angle between these two vectors are 90 degree. So the cos 90 would be the 0. Just look at and recall the definition of dot product. Similarly, z cap with the dot product with the x cap would be also be 0, and x cap dot product with x cap would giving you the 1, because the angle between these two vectors would be the 0, so the cos 0 would be the 1, and the magnitude of x cap and x cap is also 1. So you would be ending up with value called ax. So the dot product of this vector a with the x cap would be simply ax. Similarly, the dot product or the projection of the vector a towards the y cap would be ay, and the projection of vector a towards the z cap will be simply az. Okay, so these ax, ay and az are the simply projection of vector a towards the x-axis, y-axis and the z-axis respectively. Okay, so just keep these definitions and the points in your mind, because when we are dealing with certain application of electromagnetic theory, we will be using these frequently. Okay, so just keep these points in your mind. Okay, fine. Now let's talk about triple products, scalar triple products and the vector triple products. So in the last class we discussed about the cross product for two vectors b cross c. We have talked about. Yes, now this cross product is also called the vector product. So this is b cross c is itself a vector. Yes, because the result of this b cross c would be giving me a vector. Now if this is a vector, we can do operation with this vector with another vector. So like we can do dot product with this vector, we can do the cross product with this vector. So you know, dot product is also called a scalar product. Now that's why we are calling it a scalar triple product. Triple because there are three terms involving in this dot product, and a scalar because the result of this overall dot product would be my scalar quantity. Okay, always remember the result of the dot product is always a scalar quantity. So now let's talk about this scalar triple product in terms of the geometry, because when you relate these dot product and the cross product in terms of the geometry, it is very clear in your mind. You do not have to mug up the definition. Okay, so let's talk about this. So mathematically you can calculate this triple product by calculating this determinant, but I want to discuss geometrically what does this mean. So we discussed in the last class that this b cross c or the cross product of these two vectors will give me the area of the plane or the area of the parallelepiped. Okay, so sorry, the parallelogram in which the b and c are. So like this b cross c would be giving me this area of this parallelogram. Yes, so the magnitude of this cross product would be giving me the area of this. Now I am taking the dot product of A with this cross product of B and C. Now the magnitude of B cross C would be giving me the area of this parallelogram, but the direction would be followed by right hand rule. Yes, so the direction of B cross C, because B cross C would be giving me the vector, and the direction of that vector would be given by this right hand rule. Now when you take, so I think this is given wrong in this picture. Let's say this is my B and this is my C. Okay, oh, sorry, it was right. So okay, so this is right, B and C are right. Okay, so now when you will take the cross product of B and C, you will curl around your fingers of right hand towards the C starting from the vector B. Then the direction of thumb would be given in this n cap direction. Yes, and this n cap would be the perpendicular to the plane in which the B and C vectors are. Okay, so this would be the direction of B cross C vector. Now I am taking the dot product of this vector A. So I am taking the projection of this vector A onto the vector n cap. Yes, so this would be my projection. So there is one mistake you can do. When I'm taking, you are taking, let's say we are taking dot product of these two vectors A dot B, then the result is given by magnitude of vector A, magnitude of vector B, and the cosine of angle between these two vectors. Now let's say this is my vector B, this is my vector A, then the projection of vector A onto the vector B is simply A cos theta. Okay, so this A cos theta is my projection of vector A onto the vector B. So if you want to find the projection of vector A onto the vector B, then you just have to write it A dot B divided by the magnitude of B. Yes, it would be equal to A cos theta, and this is my projection of vector A onto the vector B. Yes, so but now here as I mentioned in the earlier portion also, when you are taking the dot product, with unit vector, so let's say I'm taking the dot product of A dot this n cap. Yes, here I want to take the dot product of A with this n cap. Now this would simply give me the magnitude of A, magnitude of n cap, and that cosine of that angle between this A and this n cap. Now this would be simply 1. Okay, so this will be remaining A cos theta, and this is simply the projection of vector A onto the n cap. Okay, so when you are taking projection of a vector onto the unit vector, then you do not have to divide by vector B, or let's say even if you divide by n cap commode, then you will be simply ending up with 1. Okay, so just remember this point. When you are taking a projection of vector onto the unit vector, then you just have to dot product. You just have to take the dot product. Okay, just simply remember this. So now when I'm doing A dot B cross C, that means I have to make the dot product of A with this B cross C vector. Now B cross C is simply in this direction, n cap. Okay, so I just have to take the projection of vector A onto the vector n cap. So this would be simply giving me this much of length. Yes, so this would be my projection of vector A. So overall, this A dot B cross C, so B cross C gave me the area of this parallelogram, and A dot B cross C would be giving me the projection of vector A times the magnitude of this vector B cross C. So simply this area times this height. Yes, and this would represent the volume of this parallelopiped. Okay, we call this parallelopiped. So this area of the base times the altitude of this parallelopiped would be simply the volume of this parallelopiped. So what I want to say that geometrically A dot B cross C would be giving you the volume of the parallelopiped formed with A, B and C. Okay, that's it. Now mathematically you can do the calculation with this help of this determinant. Now this equation here, would hold true, because you can prove it in either way. Either you can prove it geometrically or you can do it mathematically. I would give you the proof in mathematical way. Okay. Now, as I mentioned, this A dot B cross C is giving you the volume of this parallelepiped. Now let's see what does B dot C cross A gives. Now C cross A, let me remove this. Now C cross A would be giving you the area of this side, this plane, okay? This side of the parallel pipe. Now when you will take the dot product with B, so it will give you simply this side, okay? Because the direction of A cross C would be in this direction, and then when you will take the projection onto this B vector, then you will simply find this side, okay? So again, this would be this area multiplied with this height, let's say h, then again it would be giving me the volume of this parallelepiped. Yes, similarly this C dot A cross B would also give me the same volume. So in this way, this equation would, or this relation would hold true. So just remember, A dot B cross C is equal to B dot C cross A is equal to C dot A cross B. In terms of memory, you can just look at this expression. These are in the cyclic manner: A, B, C, B, C, and then A. If you start with C, A, and B, so A, then B, and then C, and then A. Okay, so in this way you can remember this equation. Now we can also do the cross product with this B cross C vector. Okay, so A cross this B cross C. Now this is defined with so-called back cab rule. Okay, back cab rule means this is back and this is cab. So just remember this equation, we will be using it frequently. This is very important equation. I am not giving you any proof for this because it would be very lengthy, and I do not want to go into much more mathematics because it is not needed for us for this electromagnetic theory. Okay, so just remember this back cab rule to find the vector triple product. Okay, so this is a little bit about the vector calculus. Maybe in the next lecture we will be talking about some positional vectors and how these vectors are transformed, because we sometimes get the question in the gate related to the transformation. Okay, and maybe later we will be defining some cylindrical coordinate system and like so. Okay, so thank you.